Today on AI Paper Podcast, we are unpacking a paper called DDI Dynamic Patch Scheduling for Efficient Diffusion Transformers. It is from researchers at Boston University and Amazon, specifically Dahi Kim, Deepti Gadiyaram, and Raghu Deepgadi.
Right, and the core issue they are tackling is the massive computational weight of modern diffusion transformers like FLUX.1 and WAN 2.1.
Because currently these models use a fixed patch size for tokenization across the entire denoising process, meaning a simple prompt like a blue sky gets the exact same computational treatment as a highly complex crowded zebra scene.
Which is obviously inefficient. So their solution is DDiT, a training-free test time strategy that dynamically adjusts those patch sizes based on both the content complexity and the specific denoising time step.
Yeah, it uses larger patches for the coarse global structure in the early steps, and then shifts to smaller patches for fine details later.
And the results are impressive. They see up to a 3.52x speedup on FLUX.1 dev for text-to-image generation, and the 3.2x speedup on WAN 2.1 for text-to-video.
All without degrading perceptual quality, CLIP scores, or prompt adherence. It is a massive efficiency win.
It really is the kind of optimization that takes a heavy research model and makes it actually usable.
All right, so to kind of take a step back and look at why this matters for you, the listener, if you have been running these open source models locally, you probably know this pain intimately. The paper highlights a very specific metric that just hurts to read.
I know exactly the one you mean.
Yeah, generating a single 5-second video clip at 720p resolution using WAN 2.1 on an RTX 4090 takes about 30 minutes.
Yeah, 30 minutes for 5 seconds. And keeping in mind that the 4090 is basically a $2,000 top-tier consumer card.
Right.
It is a massive bottleneck. It is what keeps these models locked in the lab and out of real-time interactive applications. Even for image generation with FLUX, if you push the step count high enough, you literally have time to go make a coffee while it runs.
Exactly. So before we really get into the how of DDiT, we need to look under the hood at the why. Like, why are these architectures so incredibly heavy? We know transformers in general are compute hungry, but what is specifically clogging the pipes here?
It all comes down to the fundamental architecture of the diffusion transformer, or DIT. If you look at how FLUX or SORA or WAN works, they do not look at an image as a traditional grid of pixels, like older convolutional networks did.
They treat the visual data as a sequence of tokens.
Precisely. They chop the image, or, well, technically the noisy latent representation of the image, into these little squares called patches.
Typically like a 2x2 grid, right?
Correct. So for a standard high-res image, you are generating thousands of these patches. And each one of those becomes a token that the transformer has to process. And here is the real kicker. The attention mechanism, which is the core mathematical engine of the transformer, has a quadratic computational cost.
Which is the classic dole-around problem, meaning if you double the number of tokens, you do not just double the workload, you quadruple it.
Exactly. N squared is the absolute enemy of scaling. And the fatal flaw in current DDiT architectures, the reason you are sitting there for 30 minutes waiting on a short video, is that they are totally rigid. They use that exact same fixed patch size for every single step of the generation process.
So whether it is step 1, where the image is literally just static noise, or step 50, where it is refining a tiny sub-millimeter detail on a character's face, the model is doing the exact same amount of math.
It is doing the exact same amount of heavy lifting, regardless of what is actually happening in the image.
I really love the analogy from our prep notes for this. It is like painting a wall.
Oh yeah, the painting analogy is perfect for this. So imagine you are hired to paint a mural on a massive wall. The mural is mostly just a giant solid blue sky, but down in the bottom right corner, there is this tiny intricate figure.
Right.
Current diffusion transformers are like forcing the painter to fill in that entire mass of blue sky using a fine point ballpoint pen.
Which works. I mean, the wall eventually gets painted blue.
It gets blue, but it takes an eternity. Millions of tiny dots. When any rational person would just grab a paint roller for the sky and then switch to the fine point pen for the detailed figure in the corner.
Right, and that is essentially what DDiT is doing. Dynamic Diffusion Transformer, it gives the AI model a paint roller.
It gives it a roller, and it tells it exactly when it is safe to use it.
Which leads us directly to the core intuition of this paper. The researchers argue that visual generation is inherently hierarchical. It is not this flat, uniform process that happens all at once.
Definitely not. Think about how an image actually emerges from pure random noise during diffusion.
Yeah.
In those very early time steps, the model is not drawing fine details, It is laying down geometry.
It is doing the coarse structural layout.
Exactly. It is deciding this half of the frame is dark and this half is light. Here is the horizon line. These are very low-frequency, blurry concepts. You absolutely do not need millimeter-level resolution to decide where the sky goes.
So at that early stage, taking those tiny 2x2 patches and grouping them into much larger patches, say 4x4 or even 8x8, should not theoretically damage the final output at all.
It really should not. You are just aggregating the signal while the signal itself is still very broad and fuzzy. But then as you move further through the denoising process, as the image clears up and solidifies, you naturally start needing to resolve high-frequency details.
And that is when you swap the paint roller for the ballpoint pen.
Right. That is when you drop the patch size back down to capture the sharp edges and the textures.
You know what I found super fascinating about their approach was the prompt sensitivity aspect. Because under the current standard paradigm, if I ask FLUX for a prompt like a plain white wall, or I ask it for a chaotic cyberpunk city at night, the inference time is completely identical.
Which is mathematically absurd if you think about it.
Right?
A plain white wall has almost zero information density. Why on earth are we burning premium GPU cycles, analyzing the high-frequency texture of literal nothingness?
And the paper actually proves this out. They ran a whole prompt sensitivity analysis comparing their method to previous optimization attempts.
Yeah, they show that existing acceleration methods, things like token caching or basic pruning, are usually completely agnostic to the actual prompt you feed them. They just run a hard-coded, rigid schedule. But DDiT is deeply adaptive. If you give it that simple blue sky prompt, the model recognizes that the internal latent representation is structurally simple.
So it just sticks with the large patches, the roller, for almost the entire generation process.
Exactly. But if you throw a complex prompt at it, their stress test in the paper was a scene crowded with many zebras.
Which is just a nightmare of high-frequency stripes.
Total nightmare. The model detects that high variance immediately. It sees the complexity forming and switches to the small patches much earlier in the timeline to make sure it captures all those interlocking stripes perfectly.
And just to ground this in some hard numbers for you listening, the paper notes that if you increase the patch size from P to 2P, the total number of tokens drops by a factor of 4.
Because of the grid geometry, yeah.
Right, and because of that n-squared quadratic attention cost we mentioned earlier, dropping the token count by 4x yields a massive computational gain.
It practically translates to a 3x speedup for those specific time steps where the model decides it can get away with the larger patches.
Okay, so intuitively this makes absolute sense. Big patches for the easy broad strokes, small patches for the complex fine details. But the real engineering hurdle here is how does the model actually know? Because there is no human in the loop sitting there watching the image render saying, okay, switch to high resolution now.
Right. It has to be fully automated, and more importantly, it has to be computationally cheap. If you have to run a massive secondary neural network just to analyze the image and decide how to save compute, you end up losing all the time you were trying to save.
You defeat the whole purpose of the optimization. So they needed a lightweight signal, a mathematical trigger.
And this is where I think the paper gets genuinely brilliant with the math. They decided to look at the latent evolution.
Walk us through what that actually means in this context.
So as the diffusion process steps backward from pure static noise to a clean image, the latent, which is the highly compressed numerical representation of the image, is constantly moving and changing. It is basically tracing a path through a high-dimensional mathematical space. The authors hypothesized that the speed and the nature of how that latent changes tells you exactly how hard the model is working to build structure.
So if the latent representation is only changing slightly from step to step,
then the model is likely just stabilizing those coarse global structures. It is coasting. It is safe to use the big patches.
But if it is changing wildly,
then it is a volatile period. The model is actively resolving complex, intricate features, and you absolutely need the small patches to capture that rapid evolution.
No, to actually measure this, they use a finite difference equation. And I want to dig into this because they did not just measure the speed of the change, they looked at acceleration, and then they went one layer deeper than that.
Yeah, this is arguably the aha moment of the entire methodology. They treated the denoising trajectory like a physical moving object. First, they calculated the first-order difference, which is essentially velocity. How much did the latent change moving from timestep t to timestep t minus 1?
But they found that signal was way too noisy. Right?
Way too noisy. Because diffusion is fundamentally a stochastic process. It has random noise injected into it by design. So the velocity signal is just jittering all over the place. It is not clean enough to base scheduling decisions on. So then they tried the second order difference, which is acceleration.
Still too noisy.
Still too influenced by the global noise schedule. So they took it one step further to the third order difference. In physics terminology, that's called jerk.
Right, the rate of change of acceleration.
Yes, exactly. And it turns out that in the context of diffusion transformers, the third order difference acts as an incredibly pristine filter.
But why, though? It feels a little arbitrary to just keep taking derivatives until you find one that works. Why is the third order the magic number for diffusion?
It actually makes a lot of sense when you approach it from a signal processing perspective. It is all about separating the global drift from the local detail. The first and second orders are heavily dominated by the smooth, macro-level drift of the diffusion process. Just the basic mechanical action of the model slowly pushing the noise toward the clean image manifold. That smooth drift is so loud it completely masks the subtle signals of detail emerging.
Ah, I see.
But when you calculate the third order difference, it acts as a high-pass filter. It completely cancels out that smooth, consistent drift.
Leaving only the sudden deviations.
Exactly. What is left over is the deviation from the smooth path. A spike of the third order difference means the model is suddenly changing direction or rapidly shifting intensity in a specific conceptual area. It is essentially the model screaming something complex and important is forming right here, and I need granularity right now.
That is just surprisingly elegant. They are essentially using basic calculus to listen to the heartbeat of the generation process.
It is a beautiful application of classic math to a modern deep learning problem. And the best part is because it only relies on latents from previous time steps that you already computed, it is almost completely free to calculate. You just store the last couple of steps in memory and do a couple of quick subtractions.
So that solves the win. That tells them what time step to switch resolutions at. But they did not stop there. They also validated this signal to determine exactly where in the image to apply the detail, which brings us to their spatial variance estimation.
Right, because obviously, even in a highly complex image, not every single section is complex. They have this great visual example in the paper of an astronaut riding a horse.
Classic AI prompt.
A total classic. Now, the astronaut themselves has a massive amount of detail. You have the fabric folds on the spacesuit, the reflections on the visor of the horse's mane.
But the background behind them is just a dark, smooth, blurry gradient.
Exactly. So what they did is look at the acceleration signal inside the individual patches themselves. They compute the standard deviation of this acceleration across the spatial dimension of each patch.
Meaning, if the deviation is high inside a patch,
it means the individual pixels or sub-features inside that patch are fighting each other. They're evolving at wildly different rates, which tells you there is a sharp edge or a complex texture forming there. You need small patches.
But if the standard deviation is very low,
then all the features in that patch are moving together uniformly. It is a smooth surface, like the background of that astronaut image. Or they show another example of a smooth red apple. You can safely aggregate those areas into big patches without losing anything.
And this spatial variance test essentially confirms their hypothesis. It shows that the zebra prompt triggers high variance across the entire grid, while the red apple prompt triggers almost completely low variance everywhere.
It perfectly validates that their third-order jerk signal is genuinely tracking semantic complexity. It acts as an automated dynamic roadmap for the model's computational budget.
Okay, I want to pivot over to the practical results side of things. Because as anyone in software knows, whenever you hear the word optimization, you usually brace yourself for a quality drop. The old saying is, fast, good, cheap, pick two.
You are generally right to be skeptical. But DDiT really seems to be bending that rule. The empirical results they outline are frankly startling.
Let's hit the speed numbers first.
On FLUX 0.1 dev, which is their primary text-to-image testbed, they achieved up to a 3.5 2x speedup. And on 2.1 for video, they hit a 3.2x speedup.
So that agonizing 30-minute wait time for video drops down to under 10 minutes.
Which is a complete paradigm shift for the user experience.
Oh, absolutely. Waiting 30 minutes is an asynchronous task. You hit generate and you go do laundry or run errands. But waiting 9 minutes? That is interactive. You go grab a glass of water, check an email, and your video is ready.
It changes the entire workflow.
But the real question is, does the resulting video look like compressed garbage? Because a 3x speedup is usually exactly the point where you start seeing heavy artifacting and blurry edges.
And that is the wild part. It really does not. They have a ton of visual comparisons in the paper, and one that stands out is a generated image of a sloth wearing a knit hat.
Which is basically a torture test for compression algorithms.
It really is. You have the messy, unkempt fur, the intricate repeating pattern of the yarn, the weird lighting. And if you look at the baseline generation next to the 3.5x accelerated DDiT version, they are perceptually indistinguishable. The knit pattern on the hat is totally crisp. The individual hairs on the fur are distinct.
And they back this up with objective metrics, right? It is not just the researchers squinting at JPEGs and saying, yeah, looks good to me.
No, they did rigorous quantitative testing. For the FLUX model, they used image reward scores. The baseline unoptimized model scored a 1.0291. The heavily accelerated DDiT version scored a 1.0182.
Okay, so that difference is statistically negligible.
Completely negligible. And for the video benchmark, they used VBench. The score only dropped from an 81.24 down to an 80.53.
I mean, in the world of AI benchmarking, dropping 0.7 points on a test to instantly triple your inference speed is a trade literally any engineer would take every single day.
Instantly. It is an absolute home run trade-off.
I want to clarify something for you listening if you happen to be familiar with other transformer optimization techniques. How exactly is DDiT different from something like token pruning? Because I have used things like token merging or windowed attention in the past, and sometimes the image context just completely falls apart.
That is a highly crucial distinction to make. Token pruning approaches are fundamentally subtractive. They run an algorithm to identify tokens they deem unimportant, like the solid blue sky in the corners, and they just delete them. They completely stop processing them.
Which has always sounded incredibly risky to me.
Because it is risky. Context matters heavily in visual generation. Even a totally blank white background token contributes to the global lighting and color balance of the overall scene. If you just aggressively delete those background tokens, the model suddenly loses its contextual grounding.
Right, you end up with weird lighting artifacts or subjects getting strangely cut off.
Exactly. You disrupt the global receptive field. But DDiT is not deleting anything.
It is aggregating.
Yes. When it decides to use a large patch, it does not throw the pixel data in the trash. It mathematically averages their features into a single, richer, localized token. So the transformer still sees the entire sky. It just processes it as one unified sky concept rather than 16 redundant individual sky squares.
So the global context is perfectly preserved.
Completely preserved.
Yeah.
That is why you do not see the bizarre structural artifacts that plague aggressive pruning methods. It is a smart compression of redundant data rather than a risky deletion of it.
Let's talk about the actual implementation process, because you mentioned way at the beginning of the episode that this is training free, which is obviously a massive buzzword right now. But why does it matter quite so much in this specific context?
Because training these frontier models costs literally millions of dollars in compute. If you had to retrain the underlying weights of FLUX or 1 to natively understand dynamic patches, you would need a massive cluster of H100 GPUs running at full tilt for weeks. Very few organizations have the budget or the time for that.
So DDiT acts more like a plugin?
Essentially, yes. It is purely an inference time strategy. You can take the exact FLUX model weights you already have sitting on your local hard drive, apply this dynamic scheduling algorithm to the generation loop, and boom, you get the speed up immediately. You do not touch the pre-trained weights at all.
That makes it incredibly deployable. If I am a software engineer at startup trying to build a generative video platform, this is absolute music to my ears.
Because it translates to direct immediate cost savings. If you are serving these models in the cloud via an API, cutting your inference time by 66% means you are literally cutting your cloud GPU bill by 66%.
That is often the difference between a viable, profitable product and a complete money pit.
Absolutely. And for the regular consumer, it brings us so much closer to a reality where we can run these models locally without melting our hardware. Right now, running WAN 2.1 is basically a hobby for the rich or the extremely patient.
Right.
But if you take DDiT and combine it with maybe some heavy quantization, lowering the precision of the floating point math, we could realistically see high-fidelity video generation happening on a high-end consumer laptop in the very near future.
It really feels like we're officially entering the efficiency era of AI development. Because for the last 3 or 4 years, it has just been the brute force era.
Oh, yeah, entirely brute force. Just throw more compute at the problem,
Yeah.
make the parameter count bigger, scrape a bigger data set,
And we are rapidly hitting the physical ceiling of that strategy. We're running out of power grid capacity. We are running out of silicon. Now the industry has to look under the hood and ask, are we actually being smart about how we process this data?
And DDiT looks at the DIT architecture and says, no, you are being incredibly wasteful. We have been severely micromanaging the model, forcing it to intensely scrutinize every single pixel at every single microsecond of generation. DDiT proves that if we trust the underlying architecture, if we let the model be strategically lazy, it can produce the exact same quality in a fraction of the time.
Strategically lazy. I really like that framing. It is like skimming a textbook. Yeah. You do not read every single at the end and with deep, intense focus. You skim the filler words and you slow down to focus your cognitive energy on the actual complex concepts.
That is a perfect parallel. And, that actually brings up a really interesting point about where this core philosophy goes next, because this fundamental idea of dynamic compute scaling based on complexity, it really should not be limited just to image or video generation.
Right. Which leads me to a final thought I want to leave you, the listener, with today. We have spent this entire deep dive talking about inference, making the model run faster after it has already been fully built. But if this dynamic hierarchy, this transition from coarse global understanding to fine localized detail, is truly fundamental to how models learn.
Oh, I see exactly where you're taking this.
Yeah, what if we apply this to the training process itself?
Which is the trillion-dollar bottleneck right now.
Exactly. Training is vastly more expensive than inference. Imagine a training curriculum where a foundational model starts its life learning exclusively on massive aggregated patches. It learns the broad global structures of the visual world incredibly quickly and cheaply.
And then as the training progresses, you dynamically drop the patch size down to force it to learn the fine details.
Right, like how a human artist sketches. You never start a portrait by rendering the individual eyelashes. You block out the shape of the head first.
But currently, we force these massive AI models to calculate the eyelashes from Epoch 1 of training. If researchers could figure out how to weave a DDiT-style dynamic resolution schedule directly into the multi-week training loop,
you could potentially slash the baseline cost of creating these foundational models by an order of magnitude.
You would stop wasting millions of dollars of GPU cycles, forcing the model to learn what a plain blue sky looks like at 4K resolution for 10,000 steps.
Yeah.
You just speedrun the easy concepts and save your training budget for the complex textures. The authors briefly hint at this potential in the paper, but to me it is the most obvious and exciting next step.
So if anyone listening is currently sitting in a lab at Boston University or Amazon, please get right on that. We all desperately want cheaper training runs.
Seriously, the global electricity bill is way too high.
All right, so to quickly recap everything for you before we go, DDiT is a new, highly adaptive way to run diffusion transformers. It monitors the third-order difference of the latent space, essentially tracking the jerk or sudden volatility of the image formation, to decide exactly when to group pixels together and when to focus in on details.
It takes a rigid, inefficient process and makes it beautifully dynamic.
It triples the generation speed of state-of-the-art models like FLUX and WAN with effectively zero hit to visual quality. And you can plug it into your existing workflow without retraining anything.
It is one of those rare, pure win-win scenarios in AI optimization.
For those of you who really want to get into the weeds on that third-order finite difference math, because it genuinely is an elegant piece of calculus, we highly encourage you to go read the full paper. It is a fantastic showcase of how a little bit of clever math can save a massive amount of hardware compute.
Truly elegant engineering.
And that wraps up our deep dive on DDiT. Thanks for tuning into AI Paper Podcast. Keep experimenting with your models, and we will catch you on the next one.
See you next time.